Okay, let me start. Today we are going to talk about the training neural network, loss function, fetch normalization, and regularization. We will study the practical technique to train the neural network in terms of the loss functions, the fetch normalization, or the regularization techniques such as the data augmentation. So, okay, let's do that. So before starting, let's recap what we have done so far. So yeah, this is lecture 10, right? So in last week we talked about the what is the deep neural network. So comparing to the perceptron or the multi-output perceptron or the multi-layer perceptron, deep neural network consisting of the several kinds of the hidden layer with some deeper weight functions, right? But when I think about the deep learning on large scale inputs such as the image, the conventional neural network has the too many parameters we have to find out. So we need a more clever way to deal with this, right? So we introduced the convolutional neural network that process the data in a local manner, right? So the local processing of the data have the parameter sharing and sparsity of the connection properties, right? So this is the convolutional neural network. So actually the convolutional neural network has some a bit of a history, but the AlexNet in 2012 was the first time to perform well with the convolutional neural network. So I think it is start point of the recent deep learning techniques. Right? So it was the AlexNet, right? So nowadays the ConvNet are used in everywhere in object detection or semantic segmentation, self-driving car, something like this, right? Image captioning, even for style transfer, right? So okay, so what was the convolution? Comparing to the neural network or the perceptron that need the 10 by 3072 parameters weight to deal with the input and some kind of activation like this, right? So it is really hard to deal with. So we introduced a more clever way to deal with this perceptron. So we call this uh, we call this computation as a convolution, right? So if we have the input signal like this, in this case image, right, and we introduce a small scale filter that convolve with the image in the way that we can slide over the image, especially computing dot product. So this is the convolution, right? So yep. So yeah. So to train the training the neural network means that we have to find out the filter weight here, right? So in this case, a 5 by 3 filters to process the image of the 32 by 32 by 3. So yeah, it is the network parameter, right? So what I want to do? So we can convolve this local filter over whole special location, something like this, right? So finally, we can find out the activation map from the input image with the local small filter, something like that, right? So in this case, we can make 28 by 28 by one activation map, right? So this is just one channel in arbitrary activation map, right? And then if we can use another filter, something like, in this case, green filter, comparing to this one, right? Then we can make another activation map, right? So by using the several successive subsequent convolution filter, in this case, 5 by 5 filter, we will get the 6 separate activation map, something like this, right? So from 32 by 32 by 3 input image or activation map, by using the one convolution layer, we can generate the 28 by 28 by 6 activation map, right? So it will be the another activation map which will be used in the next convolutional network. Okay, so yeah, so what is the convolunet? So convolutional neural network is the sequence of the convolutional layer inspired with the activation functions such as the value, right? So as you can see here, from the input image or the input signal, by using the convolutional layer and the value function, we can generate another activation map, right? And by using the another one more convolution layer, we can generate another activation map, right? And by stacking those kinds of the convolution and value function, we can finally generate or the estimate our final output from the input image or the input signal, right? So this is the general formulation of the convolution neural network, or just called the convnet, right? So if you see the convnet in detail, you can see those kinds of the how to say, those kinds of the activation map, right? So as you can see here, from the input activation map, by using the network parameter which are trained during the training procedure, we can generate the output activation map per each filter, right? So in this case, we have the 32 filters. That means we can generate the 32 activation maps, something like this, right? So the shape of the activation map should be like this, right? So if you see the convolution in detail like this, it is related to the convolution of the two signal. In this case, F is the input activation map. G means the convolutional network parameter, right? So in today's lecture, we will derive the way to train the neural network. So we will come back here to understand the convolution, right? So it was the convolution. So by stacking the convolution layer, we can generate the hierarchy of the convolution layer. So as you can see here, by stacking the convolutional neural filter, we can see the hierarchical semantic meaning from the input signal. So as you can see here, in the higher level feature, there exists some semantic information from the image, but when you see the low level feature, there only have some kinds of the low level statistics such as the edge or the some kinds of the Gaussian blur or something like this. So beauty of the convolutional network is that we can extract the low level to high level features in a hierarchical manner, right? So this is the deep convolutional neural network, right? So, and we also talked about the how to compute the output resolution exactly, right? So as you can see here, yeah. Here, generally, when we design the one convolutional layer, we have to choose the size of the filter and the stride and the padding, right? So if we have the the FIF filter with the stride S with the pad P pixel, then output of the n by n input activation map should be practiced, right? So I guess you might derive this one yourself. So if you're not, please do that because it is really important. Because when you design the neural network, if you use some kinds of library such as the PyTorch or the TensorFlow, you don't need to consider this one, right? Because this one is computed in the framework in the framework, but if you don't understand this part, you might not understand what's going on your deep network. So please try to derive this one yourself, right? So yeah. then there is one more concept, the pooling layer, right? So why we need the pooling layer? It can make the representation or the activation smaller and more manageable, right? So it operates over each activation map independently, as you can see here. In the case of the what is that? Maybe max pooling, right? So if we use some kind of pooling on input activation map, we can generate the new activation map, something like this, right? So yeah, we generally use the max pooling or the average pooling, right? So yeah, it is the general architecture of the deep neural network, right? So actually the deep neural network looks very complicating, but if you see detail, there are only convolution value or some kind of pooling layer with some connectivity, right? So it means that if you understand what is the convolution layer value and pooling, then you can understand everything in your network. Okay. So and then we also talked about CNN architecture. First one was the LNet, right? And second one is AlexNet, right? If you see the detail in AlexNet, the architecture design consisting of the input, in this case output channel, right, with the filter size with stride and fat, right, or and max pooling and pooling layer, right? So it means that to understand the deep neural network, you can just to see the connectivity between the convolutional layers and the max pooling layer and normalization layer with their specific parameter, right? So it was the AlexNet, right? And then we also talked about very successful deep neural network called the LessNet, right? So the conventional plane layer, as you can see here, in LessNet or LegionNet, use the Legion mapping to train the output here. So there is the one more connection from input to output here. So by connecting input to output, we can just estimate the residue here as the output of this convolution layer, which will have to train the network more effectively and efficiently, right? So this is the deep residual network, right? Actually, the deep residual network is the most cited paper in whole area in the Google Scholar Matrix in 2019, maybe 2020 as well. And it is used in vision, language, speech, AlphaGo, something like this. So yeah, I think that this paper is one of the most successful paper in the deep learning area, right? So I highly suggest you to read this paper. Actually, this paper is well written, well written, so you can easily understand what they mean. So you please try to understand this paper yourself, right? So yeah, and then there are another so many network architecture, such as here like this, and then yesterday there was the ECCB 2020 rebuttal period, right? So in this year there are more than what was that? More than 6,000 papers in ECCB 2020, right? So it means that there might be so many other network architecture in the ECCB conference. So yeah, now we are living in the deep learning world. So yeah, let's see. So yeah, it was the last week the lecture. So today we will start the training the neural network. Okay. So yeah, let's start. Okay, let's recap the procedure of the neural network. Okay, so given the training set, xn and yn, xn is the input signal, right? Yn is the output signal, right? In regression case, ym means some kind of the continuous variable, and in the classification case, ym will be the some kind of the class label, right? So given the training set, what we want to do is to design the deep neural network as the function fw of the xn, right? So in this case, w means the network parameter, right? Network parameter, and the shape of the network parameter or the network architecture of the deep neural network is something like this, something like this, something like this, right? So the architecture of the deep neural network might be varied depending on their application, but as we discussed previously, if you see the here, the only learnable parameters network, the convolutional parameter, right? So in this case, we want to estimate we want to train the network parameter w during the training time, right? Okay, so from the input xn, we design the deep neural network with the parameter w, and then we have to define the loss function with the ground truth yn corresponding to xn, right? So yeah, so to train training this deep neural network means we should find the network parameter w that minimize this loss function, right? So the goal of the training the neural network is exactly same as the linear regression, logistic regression, SVM, that we've discussed so far, right? So yeah, so it means that first of all, we have to define the loss function, right? So which loss function we have to use, right? And then what do you want to do next? Then we have to design the training strategy, right? Training strategy. So such as the gradient descent, right? The third one is to update the network parameter w. We need the derivative of the loss function in terms of this parameter, but the complexity of the network is really high and complex, complicating. We need a very, the fancy way to train each parameter w. So we need some kind of the let's just say the compute gradient. So right, so compute gradient, and then by using this one we can train the network very efficiently, but there are some kinds of issues, so we need a more systemical way to stabilize the network training. So we will learn the compute gradient and stabilization, right? And then in the testing time, if we let's say this is the training procedure, right? So and then if we have the test image by using the trained model here, we can generate the output to the testing image, right? In this case, there are some kinds of issue. So how can we improve the testing? How can we improve the testing accuracy? Right? And how can it transfer the pre-trained neural network to the another task? So it is called the transfer learning things, right? So this is a general overview of the today's lecture. So let's see each step. Okay, so let me start. So first of all, let's think about the loss function. So to train the neural network, what kinds of the loss function or the distance function should be used? So if you go back to our previous lectures, there are several kinds of loss functions such as the MSE for the linear regression or the logistic regression for the classification problem, right? And hinge loss function for the SVM, right? So in this neural network or this deep convolutional neural network, we can use the same loss function. I mean, we don't need to any specific loss function for the deep neural network. We can use any kind of loss function to train the neural network. So for example, your problem is the regression problem, then you can easily use the MSE, which is defined something like this, right? So this is output of our neural network or the deep convolutional neural network. From here, we can just say this is the TNN or the CNN. Okay, let me say this is TNN, right? Deep neural network, right? And so this is output of the TNN, and this is the ground truth output defined in the continuous space. So this is the just regression problem loss. What about the classification problem? What's that? We've talked about the logistic regression problem, a logistic regression function, right? What was that? What was that? If you have the input xn and some linear combination of the xn with the parameter w, and then in logistic regression we defined this nonlinear mapping function, right? So using this nonlinear mapping function, the output of this one is larger than 0, less than 1, right? So by using this one, we can compute the log probability or the log of this output, right? So why we use the log function? If you don't understand this one, please go back to our, what was the lecture 4, lecture 3 or 4, maybe in lecture 3. So in lecture 3, we will discuss why we need the log function in defining the logistic regression, right? And then with the yn, ground truth yn, we can define the logistic regression function something like this, right? So in here, if yn is 1, we just use this function because this function will be 0, right? And reversely, yn is equal to 0, then we will use this function only, eliminating this part, right? So this is just a classification problem, in binary classification problem, right? But in many cases, we need multi-class classification problem, right? Then we want to extend this logistic regression function to deal with the multi-class classification problem, right? So how can we do that? Okay, that's why we need the new function called the multinomial logistic regression function. So, and then I think that this multinomial logistic regression function is one of the most one of the most popular method to solve the classification problem in deep neural network. So main idea of this one is that we want to interpret the low classifier score as a probability. So let's see what does it mean. Okay. So here is the image here. Here is the input image. Let's say xn, and we have some network, let's say DNN, and make some output, something like this. What I want to do is to interpret this low classifier output as a probability, right? But in here, it's not a probability. It's just arbitrary real value, right? Then what do you want to do? So what I can do is to use some kind of the mapping function to make this low classifier score to the probability, right? So first of all, we will use the exponential term, exponential term, something like this, right? So by using the exponential of this one, we can generate this one, right? And then we can say that this is the probability which is larger than 0, right? So we can say that this is the unnormalized probability, right? So in here, there's no negative sign anymore, right? So we can say that now we have the probability, right? And then, but as you can see here, the sum of this one, those one are not 0, right? So to make the problem tractable, we need to make this unnormalized probability that make this unnormalized probability as a probability that has the 1 as a sum. Okay, so we use the normalization. To make a probability something like this, which have the sum to 1 here, right? So this part, if we represent this part as a function, it is something like this, right? The sk is output of our network, and this is the normalization term by summation, summing the output of the other network, other output of the, let's say sj. J means the other class, right? So in this case, this summation will be the summation of this one, right? So this is just for the normalization. Then by dividing this one to this one, we can say that this is the probability of the y is equal to k given x is equal to xn, right? So this is called the softmax function, right? So this softmax function is frequently used to make the output of the signal into the transfer or the convert the output of the signal to the probability, right? So in this case, we make this output as a probability like this, right? And then what do you want to do? And because we already know the ground truth probability, right? Because we already know this image is a cat, right? Then we can say that the collect probability is something like this, right? And then the question is, how to minimize this probability, estimated probability, and ground truth probability, right? How can we do that? So to solve this one, there are several kinds of the method to measure the distance between probability, right? So there are several kinds of the method to derive this one, but this is out of scope of these courses, but if you compute this one, to make this one similar to this one, this one and this one, this one and this one, we have to reduce the role of this term and improve this one, right? So actually this one is related to the function log in the logistic regression term, right? In other words, the probability of the yn given xn by using the negative log for this one, we can define the loss function for this classification term, right? So in other words, by minimizing, say, log this one, by minimizing this one, we can train the network. We can train the network from the input to the output here. So here is the network, right? So by using this loss function, we can train this network, right? So this is the multinomial logistic regression. Then if we derive this multinomial logistic regression, it looks something like this, right? So yeah, here. Okay. So to summarize, we have the softmax term from the output of the network. Then what we want to do, because we already know the y is equal to yn, right? Then we want to minimize negative log of the probability y is equals yn given x is equal to xn, right? So in other words, if we define this one here, then this final loss term is negative log of this one, right? So in this case, this is called the multinomial logistic regression, right? So what I want to do is to estimate the network output, and then using the softmax, and then using the minus log here to define the loss term, right? This is called the multinomial logistic regression. So comparing to the previous logistic regression, if you just considering this one, actually this is also looks like the probability, right? Because it is defined in the 0 and 1, and the sum of this term and this term is 1, right? And then this is the just ground truth. This is defined by ground truth, right? So this is a logistic regression, and this is a multinomial logistic regression. If we simplify this multinomial logistic regression as a binary classification problem, the shape of this one is not exactly same, but almost exactly same, right? So please derive this one as a two-class classification, and check this one is the same as the original logistic regression or not. Okay, so please do it yourself. Okay, this is called the multinomial logistic regression. So to summarize, to train our network, there are two kinds of the very well-known loss function. The first one is the MSE, right? Just MSE, right? For the regression problem, and for the classification problem, if your problem is the binary classification, you can use the logistic regression, and your problem is the general multi-class classification problem, then you can use the multinomial logistic regression problem. Logistic function defines something like this, right? As I mentioned previously, actually you don't need to derive this one. Actually you don't need to remember or the calculate this loss function every time yourself, because if you use some kind of the deep neural network library such as the PyTorch or the TensorFlow, they just compute this loss function in their inner process, right? But as I mentioned previously, please try to derive this one for the first time, and then if you derive this one for the first time, then you can just use this one from then. But if you didn't derive this one, you won't understand what's going on in your loss functions during training, right? So please try to derive this one yourself, right? Anyway, so let's go back to the multinomial logistic regression term. So here are some property. So what is the min and max possible L? Min is 0 and max is infinity, right? So please check our lecture 3 to understand the shape of the log function, right? And as S will be approximately equal, what is the loss? What is the loss? Because if S is approximately equal, the term will be exactly same here, right? So in this case, it will be just 1 over C, right? So this one is the just log C, right? So this is the property of the multinomial logistic regression. Okay, so it was the loss functions, and what do you want to do next? Okay, now we have the training data and the network architecture, right? Design the network architecture, and now we have the very well-defined loss function, right? What do you want to do? What do you want to do next? We need the optimization method to train the network parameter or to minimize the loss function, right? So if you remember the gradient descent, which is one of the most popular one to train the linear regression or the logistic regression or the SVM, something like this, right? So define the general formulation of the gradient descent is something like this, right? So let's say there's a loss function here, the input xn, and this is output of the network parameter. And no, this is the output of the network of xn, right? So let's say this is the DNN with the parameter w and xn and swxn, and there is the output of it, right? So the gradient descent is repeat the gradient update through the training set, whole training set. Okay, so here I said this is a repeat. Repeat means we can update the the gradient of the loss function in terms of the wj for n time. So we can say this is just a epoch. So one epoch means, So one epoch means pass through training set. So it means that, okay, if we have the training set from n is equal to 1 to the large n, then one epoch means pass the every training set to the DNN and update the W, and then by iterating this forwarding and backward and n times, we can train the network, or we can network our machine, right? So this is just called the gradient descent algorithm, original gradient descent algorithm. Then what is the limitation of this gradient descent algorithm to train our neural network? The first one is per summation of the gradient will be expensive when n is really large. So here is the loss function. So if you define the loss function, we have to aggregate the loss function defined at each sample, something like this term, right? Because this is the final definition of the loss function, right? So if you just use the gradient descent, we have to compute the gradient derivative for every possible training samples, right? So it will be very expensive. So here is solution. We can approximate the summation using a mini batch concept. Mini batch of the example, something like this. So what does it mean? Okay, so let's say here is the training sample, training features, something like this. Okay, so let's say this is just xn. So in the by using the mini batch means just like the set of the arbitrary samples here, something like this, and update the parameter w using this mini batch 1, and then update with the mini batch 2, and update and mini batch 3, like this. And then by repeating for every sample, by separating the training samples as another mini batch for the next epoch, something like this, mini batch 2, then you can train the network more efficiently and effectively. So this is the main idea of the stochastic gradient descent. So if I derive this stochastic gradient more specifically, so yeah, here is the pseudocode. So for n epochs, so n epochs means pass through the whole training set in n times, and in one epoch we separate the training set as n mini batches, something like this, right? And mini batches, and update the network parameter per these mini batches, right? So it means that if you use the gradient descent and we use the, let's say, 10 epoch, then just network parameter is updated just 10 times, 1000 times, right? But if you use the 1000 epoch with the how to say 100 batches, right? The number of batches is 100. So in this case, this network is updated by 1,100 times, right? So this is much bigger than this one, right? So it means that we can update the network parameter by more effectively by increasing the number of batches, right? So this is the main idea of the stochastic gradient or the mini batch gradient, right? Right. So, by the way, if there is the 2,000 training sample, okay, let's say training samples and the number of batches, 100 batches, and then the samples in one batches, the number of samples in batches in each batch should be 20, right? Because the number of samples in batches is determined by the number of training samples and number of the batches. Okay, so this is called the stochastic gradient descent. So the advantages of the stochastic gradient descent is as follows. The first one, it is more accurate estimation of gradient than the gradient that consider the every training set, and the mini batches lead the past training, right? Because it only consisting of the small number of training set to compute this one, and it can derive the more higher iteration than the original gradient descent, right? And which enables the network can parallelize computation and significant speed increase on the GPUs. Okay, so nowadays, so almost every deep neural network framework use the mini batch concept to update their network parameters. So you can just understand every optimization technique in deep neural network just use the mini batch gradient descent, not a gradient descent. Okay, so this is the advantage of the mini batch gradient descent. So if you compute the original gradient descent with the stochastic gradient descent, or just called the SGD, the difference is something like this, right? This is original W, right? And this is the optimal W, right? Actually, it's not optimal, but here are some network parameter that make a lower value than the initial one. Then by using the gradient descent, the network goes something like this, right? But if you use the stochastic gradient descent, it will be moves very fast, and how to say it has some kind of the fluctuation, but it will be converged very fast, very efficiently than the gradient descent. Then we will stop to the minimum here, comparing to the gradient descent here, right? So by using the stochastic gradient descent, we can make our network converge it to the semi-global minimum very efficiently by using the mini batch gradient update. Okay, so this is the idea of the stochastic gradient descent. So actually, nowadays there are so many advanced optimization techniques such as the ADAM, the moment, the NJG, ADA gradient, ADA delta, RMS probe, something like this. So if you use the deep learning library, you can just to use the any kind of the well-known advanced optimization technique. Actually, those kinds of technique improve the convergence rate of the optimization technique. So there is no exact study which optimized technique is the better than the others. So, but I think it is depend on your training data set or your task. So first of all, please try to understand what is the meaning of those kinds of ones. So for detail, check out this website to understand what those kinds of the optimization means. So this is the advanced technique for the optimization of the neural network. Okay, so now we have the loss functions and the stochastic gradient descent. Then what do we want to do next? We have to compute the gradient, right? Then the question is how to compute the gradient for each parameter W over such a large complicating deep network architecture, right? So let's